Hi everyone. So today we are going to attempt the today's Leetcode problem, and it is a fresh attempt. So I have no idea about the question. I'll be attempting it from the ground up. We will be building the logic, and we will be implementing the code at the end. So I'll go through the problem. I'll read it, and you guys can also follow along with me. Okay. And the comment section is always open to you. So if you want to ask any question or if you have any doubts, you can just write it down. All right. So this is the problem of the day. What is it? It is about flipping equivalent binary trees. That's what I read from the statement. Okay, so you have a binary tree T. We can define a flip operation as follows. Choose any node, swap the left and right child subtrees. Okay, so there is some node for this tree. So this is root, and so let's say this is a binary tree. A binary tree is a tree which has, like, each node has at max two children, right? So what is a flip operation? So you can choose any node. Let's say this node is A, and this is B, this is C, and then swap the left and right subtrees. So you choose a node, you choose this node, then you can swap these trees, right? So it would be like C over here and B over here. The entire subtree is swapped, the left subtree is swapped to the right, and entire right subtree is swapped to the left, as you can see. So that's what a flip operation means, right? And then a binary tree X is flip equivalent to binary tree Y. So there's a term flip equivalent, all right? So, and a tree X is flip equivalent to Y if and only if we can make X equal to Y after some number of flip operations. Okay, so we can perform few number of flip operations like this swapping thing. And now what we are asked to do, we have to, okay, so we have given roots of two binary trees, root 1 and root 2, which is basically X and Y, and return to if the two trees are flip equivalent or false otherwise. Okay, so if they're flip equivalent, you return true, otherwise it should be false. Makes sense. Okay, so what we can do, we can do flip operations. Okay, so we have X and we have Y. So we have to make X equal to Y. So you should notice this thing. We have to make changes in X in order to make it equal to Y. So we don't have to touch Y. Okay, maybe that doesn't matter, but yeah, for the time being we have to just work on X to make it equal to Y. And now what is the next thing? Okay, so how can we move with this approach? Let me just try out test cases. So we have this tree as X and this tree as Y. These are given in the input, and okay, so this is the tree 1, this is tree 2, and here it is flippable. It is flippable because they have something here. So let's see where the lag. So basically we have to make this equal to Y, so 2 cannot be here, so somehow we need to have 3 over this place. So what they did, probably they swapped this entire thing to this side, which you can see here, and they swapped this entire thing to that side. Okay, so by making one swap operation, you can convert X to Y. And where do you make that operation? You make that operation on the node number 1, which is the root node. Okay, so that's true. Okay, so that's the thing. We have to make x equal to y. So that means these two are identical to each other value wise. Obviously, in memory they will have different locations. Okay, so now there is the time to build the logic, and we have to return a boolean, and we have given the root node of the first tree and root node of the second tree. So let's build the logic. So like we checked over here, it was possible to do that because so let's say if I build some random tree, I am really not sure what I am building, but I'm just drawing something random. So this is first tree, and this is like some other tree. So guys, what is the first condition which comes in your mind if you want to make these two structures same by doing something in this part? So the first thing which comes to my mind is the number of nodes in this region should be equal to the number of nodes in the another region. Okay, and one more thing. So this root node, it is kind of changeable. Basically, you cannot perform operation on this node because it is not a children of any other node. Because as we noted here, so you can just swap left and right subtrees, right? So basically, you are performing the operation on the parent node. So there is no parent of this node. So the first condition which I draw, like this was the first condition, this is the second condition, that root node of both of them should have same values, right? Root of 1 and root of 2 should be same, so here it has to be 1, otherwise we will just, so there are two cases. If they are equal, then go ahead with the logic, else you just return false at this place only, because they cannot be make identical later on. Yeah, now the way we move, basically if we come to this part and this part, we have to make it identical, right? So we have to make it identical. So I need to think, like, can I bring the nodes which are below this at this place anyhow? What I can do is basically I can swap these two, which will result in, if I swap it will result in 3 2. If I don't swap it will be 2 3, and then I can perform swap operations. Yeah, I want to bring some value over here other than 3. Can I do it? Other than 2, can I do it? So 2 is definitely possible because these two are left and right subtrees. If I want to bring these values, how can I do this? So let's say I brought 2 over here, and the entire structure has changed now. In order to change this, I need to change, I need to basically apply operations at this point, and it has got these two things. So I feel I cannot do this. Basically, here at this place, only 2 and 3 can be swapped. And that will give me a configuration. For the second level over here, the two nodes which we have, they should be similar to each other. Or what we can do if they are not. So basically, yeah, so we try to fix this level. If we try to fix this level, as I told you, here we have only one option. We can swap it with this one. Here we can get 2, and here we can get 3. So what we can do over here is we can just take this 2 and compare it with this one, this element. So it might be the case like there is no such node, so we'll come to that later on. Let's simplify it. So here is a node, and it is basically, let's say it's 3, let's say it's 4. So what we saw here is that in the X tree we have 2 over here, and in the Y tree we have 3 over here. So obviously this is not leading to the result which we have to make, like x is equal to y. So in that case we must swap this node. And what can we swap it with? We can swap it with this one. So we did the swap operation. Now what we see here? Now we see we get 3 over here, and here we get 2, and obviously the elements below it are still there. So now if I compare, okay, so this node is sorted. Now sorted means like this node is fixed, here is 3, here also it's 3. Now if I come to the fourth node over here, and here we have 2 which got from the swapping, which we got from the swapping. Now 2 and 4 are different. So now I cannot redo, I cannot undo the swap which I performed earlier, because that was making this condition to meet. In that case I'll just say it's not possible. So for the next level it's clear, because let's see, yeah, here let's see that for the next level it's clear that these two should be either same, or it should be interchanged. So here if we have two children, okay, so let's say it could be like this only. So let's say it's 2 and null. Here it should be 2 and null, or null comma 2. If anything like this is there, we are sorted for the second level. So I did it for the first level. For the first level, we don't need to worry about things. We just need to check if both the root nodes are same, right? Why? Because we came to know that these two nodes cannot be changed. And now when we examine the second level, we came to know that these nodes has got limited options. They can interchange values with themselves. So whatever configuration exists here, the same or inverted configuration should exist over here, right? Cool. Now comes the another part, the another level. How can we generalize our logic which we formed over there? Now we go ahead with this node and we check. So now we are examining this node. Okay, so there is one more thing which I am missing, is that we can actually make a swap over here. It will change things. For example, if I have 2 and 2 over there, here also it's 2 and 2, but these subtrees can be can be of like different varieties, right? So here there are two possibilities. First possibility is to swap, and another possibility is to not swap. There are always two cases for each node we have over here, and that will take us to some other stage. And what I feel is that it is very much unpredictable, right? So we have to consider these two cases. Okay, so basically for any node we have two options. First is swap its children, and another is no swap. Now the very important thing which we have to notice, let me delete this one. Actually this is from the previous video. So yeah, we have two options. At each node we have these two options, and these two options will lead to basically two different uh, structures, right? And if that structure is not equal to, okay, so we have this y tree over here, So if we swap this, we get some kind of structure, and this we have to check if the structure above this point is actually satisfying this. If it is, then go further deep down. Otherwise, stop exploring this path. Right? And then there's this no swap thing where we don't make any changes, and then we see if this is equal to that in any manner. If yes, then we go further. If no, so here I have a doubt. If it's a no, do we need to uh, quit, or we can move ahead without swapping it? So for the example which we had over there, so if we just swap these two, or if we don't swap these two, it is a different case, right? Okay, so how can we configure this? Basically, there's a branching. There's a branching in the code. What does that mean? Because we got two options at each and every point, and we also need to verify. Basically, we need to verify that the structure which we have formed. Okay, so there is a starting point. There's a starting tree X. We started from the root node. We made a change over there, which was basically swap, and here it's no change. So we got tree x2, tree x1, and yeah, at each point of time we have to compare it with y. If it is equal to y, then yeah, they're invertible. If it's not, then they're not invertible. So x2 is also compared with y, and here from here what we can do is basically we can keep track of what structures we have made so that we don't keep repeating it. So for that, now I think we need to cache whatever the configuration of tree we have solved. So from here also there are two steps emerging, x11 and x12. And from here also we have two cases emerging, x21, x22. How they can emerge? Basically we can make a configuration change at the root node of this. So after each transformation, that root node becomes lively. What do I mean to say? Let's say if I transformed over here, 2, 3, 4 was there initially. So I transformed, it became 2, 4, 3. Now I can basically transform these two. So it will become 2. So I can transform these children basically. So this will change. And when I make a transformation on 2 again, then it will be a completely different thing than what it was earlier, right? Because we made changes over here, and that those changes are here, which were not there earlier. It was a different case. So what does that mean? Basically, from the starting point we can make n number of changes. So there is like this. So let's say we have this tree, starting tree, which I call tx. Now we have this many options, like we have 10 n nodes, so we have n possibilities. So we performed a flip operation on n nodes and we got different tree state. And now we can compare this to ty. If any of them is equal to ty, then our quest is over and we return yes, it's true. If not, we can expand each one of them. So again, from each state there are n more possibilities. Yeah. So the state goes like this. So we have this tree state of n nodes arranged in some sort of manner. Alright, what we can do, we did some operation and this changed, right? And yeah, and we can get like as many as we want. Basically, this is the tree state, and from each state there are n branches. So it's like n, and here we got at this very step, we got here we had n branches over there, and here we got this is basically n into n square, and then if I expand it any further, it will get got n cube. So it is basically increasing at a very rapid rate. If we try to do it that way, and how many possibilities are there? Basically, we got n nodes. We can have kind of we can have, so if you consider a tree making process, if we do those swappings, in the worst case, let's say each node has two children, so we can have basically totally we can have kind of we can have like, let's say, how many configurations. So if we do the swapping thing, that will not change the. Yeah, let me think about it, man. It's a part of bigger tree. If I made some swapping over here, this entire thing is intact. It just got reversed. Yeah, so we have initial configuration of tree. Let's say it has kind of maybe, and it will be like the configuration of tree at a particular instant will be of order n. So the configuration I'm talking about is like this. We write it like this, na? One null two this. So if we just gonna swap these things, so basically these values are going to be changed, and for each place we can have n. For each place we can have n possibilities, including null and stuff. So whatever is our answer state is whatever is the state of y. We have to tell if it is possible with this kind of operation. So we have to examine kind of n to the power n states, and one of them is our y. Okay, so let me just check the constraints of this problem. Okay, got it. So we have 100 nodes over there, and each tree have unique node values in the range 0 to 100. So the keys are unique. Okay, so my bad, I should read it previously. Basically, this case is not there. This 2 thing is not there. So basically, what we got over there is they will be different for sure. So let's say in X, oh guys, wait. I can just delete this thing. It's deleted, yeah. So yeah, so let's examine this. Now we are kind of moving towards the solution. So let's say we have this node, this tree over here. So we were moving from this level to this level. So here it was 2. So it cannot be 2, right? So we have to make a decision which will not change in the future. So basically here it can be 4. And let's say in the initial, like in the Y tree, we have been given 2 and 4. In that case, we are not going to make any change at this place. If it was 4 2, then we have to say man, you have to invert it, otherwise you cannot proceed any further. So in that case also, we will say just swap this. And there's one more case where we got some foreign elements like 2 and 5. So it is clearly not possible at this stage to build, to like spawn 5 from anywhere in this tree, because you can just make transformation at this node and there is clearly no indication that we can get that. Okay, so next, moving to the next level. So here we have to check that. And there could be like only one situation. Yeah, if they are same, then we move ahead. What we have next is basically this level. And here we have more such nodes, right? So now what we will do? So we will do this. We grab the children of 2 and 4. And now we grab the children of 2 and 4 from this side. Now we got a bigger problem statement. So this is this side and this is this side. So we got like double the slots for the children, and there could be some null values as well, but we will take care of that later on. And what we can do, we should be aware of our actions. So we got childrens of 2. I call it X, Y, Z, W. What are the operations we have? So we can swap these two. We can swap, oh sorry guys, literally sorry. Oh, okay, so I'll just I can just repeat the logic. Okay, so exactly, so we were here like n to the power n states, right? Now what I thought, I drew this tree, and what I was saying here is that we have 2 and 4. So here also we have 2 and 4 in the y tree, and if we have to check at this level, there is only two conditions which are acceptable: if y is of 2 and 4, and if y is of 4 and 2. If there is any foreign element with in the y tree like 2 and 5, in that case we cannot generate 5 over here by any means, because obviously you can do transformations over here only. Now I am examining the next level. So let's say 2 has some children and 4 has some children, right? So I'm just saying x, y, z, w. So x, y, z, w is here, and obviously this y can be null because I'm just writing it over here like this. Now what operations we can do? So we can just basically swap x and y. We can swap z and w to make them equal to this equivalent, right? So it should be 4. If they are, then it's well and good. And since we know that this will be unique, why? Because you see over here that the tree will have unique node values, right? So here in this case there is no chance of repetition. So here it is not possible to repeat, like x cannot appear twice. So like there is a fixed configuration, and also x cannot appear down the trees because it's unique in the tree. Here also it's unique in the tree. So obviously these 4 nodes should be at this level, first condition. So yeah, I can see that we have to generalize the previous condition. The first condition is the nodes which are here in this part should be there in this part. So this would be kind of, I would say, order n check. Now what operations we got here is this only. We can transform these two. So first is basically check elements, same elements in both. Yeah, the order can be different, but yeah, here also we should have x, y, z and w in some other order. Now we need to say if the order, if by making these changes we can achieve this order, right? So for that the second part, which starts like this. Here, what can we do? Here, basically, we can swap things. So, how we can swap things? Basically, we can swap these two, we can swap these two. And now, if we so we can check by swapping if we are able to achieve this, which is pretty much simple, I guess. I don't think it's kind of complicated task. Yes, yes, it is simple to do. Yeah, and then we go to the next level. Here we this gets doubled. Likewise, here also this gets doubled. And the thing is, when we make a swap, the swap is kind of obviously it kind of changes the entire structure below it. So obviously it affects the tree X. Hmm? Okay, so we need to do this, and then what we can do next is basically check in the second step. Again, by making those changes, we can check if it is possible or not. And this way, when we come to the end, that will be our final destination, right? Right, that is true. Yes, that is true. But yeah, there are some challenges. Let's see how are we going to tackle that. So this is some weird test case. So let's say we are doing BFS over here. Why it is the best approach to traverse in levels, and we are going to sort things level by level. So for both trees, for each level, right? This is our algorithm. Wait, for each level, what we are going to do? First step is to, yeah, grab the nodes in sequential manner. What is sequential manner? Like from left to right, it should be the same conditions. So for example, for both of the trees, for x and y, for x, for y. So here we get the root node, and then what we do for each level is that we check elements in x is equal to element in y. A very simple check. Now, there might be the case that this could be null over here. So obviously there will be a violation, and if it's a violation, we return false. If it's a no, if it's a yes, we go ahead. What we go ahead, we push the node which has children. Like let's say, if we just did that, now we need to check if if by making some changes to adjacent elements, we can create y from x. And if that's possible, we go ahead. Otherwise, we just return false. And if you go ahead, what we will do here, so we push the children of these after making changes. After making changes, we get some, like we get x as at this level x equal to y configuration wise. Now what we can do, we can push the nodes which are not null in the queue for the next level processing. So yeah, I think I have cracked it, and I'll just write it down. Okay, so what is my logic over here? Yeah, let me just go to the problem and I just erase the things which I drew over here. I hope I don't delete the image. Pardon me, guys. I need to erase things. I cannot remove like that. Okay, yeah, it's fine. Perfect. Sorry. Perfect, I think we can write in this area. Okay, so let me write the algorithm for you, for us, basically. Okay, so what is the algorithm? Algorithm starts like this. So we will be starting with BFS, and for each level, for X and for Y, we prepare. The second step is to make the, what we call it, we make the this thing. Basically, we make this, we need to make this array, make the level nodes array. Okay, so for each level we need to make this. So basically, we in BFS we maintain a queue. In that queue we start with the root node for both the, so basically we have to make two BFS in tree X and in tree Y. So we push this q1 and q2. So we push the root node in both of them. So at each level, when we are traversing in the loop, we have the initial configuration level nodes in the queue itself. So we take out from the queue. So here we get it out from the queue, and then we run our logic. So we make this level nodes array at each level, and then we just make two checks. What are the checks? The first check is about elements in X is equals to element should be there in Y. Okay, each and every element in X should be there in Y, and we have to do this. And then we have the second check. There is some level of swapping. We prepare children array, which will be sequential, right? So for two, let's say for this level, if we prepare that array, we just keep a vector over here. So we first push the children of 4 here. If it is 4 and 5, so we push 4 and 5 over here. For 3 we have 6 and null, so we can push 6 and -1. So you see how I'm preparing this. It is basically very much sequential. So this is like we put -1 over here. That means there is no children over there. Make sense? Right. And we all know like swapping happens this way, or this way only, because these are the left and right subtrees, right? So we prepare children array at the first step. At the first step we prepare the children array, right? Oh, sorry, let me. Okay, so for the first step at each level, we check if elements in X is equal to elements in Y. In the second step, we prepare the children array. So it will be like X, XC1, children of X. This will be YC. Keep it YC only and XC. And then what we can do here is basically now in the children, now it's time to do some swapping and check if we are able to achieve this. So basically we start with each element of XC and we check if it is equal to YC at the same place. If it's not, we try swapping it. So if by swapping we cannot construct this YC progressively, if at any point of time it fails, the trees are not flippable. Okay, so here we directly return this result false. And by if we make the flipping thing, we actually change the tree structure in X, right? That's pretty much obvious. And if we make a flip at this level of point of time, the other nodes are below it, so this part has no conflicts with this change. Okay, so this is the case. If it fails anywhere, we return false. and that's how it works. If we pass this, we get the answer as true. Now let's think, what are the data structure we're going to need. Oh, so let me write this very much clean again. Just give me 1 minute to write that. Okay, so because we all know the logic. Okay, so here is how we will be approaching the solution. So first thing first, what we will be doing, we will be doing BFS in X and Y. For that, we need data structure. A data structure I'm writing in blue. There will be a Q1 and Q2, which will be storing tree node, the node of the tree. And here also, it will be storing the tree node in the queue. Standard DFS thing. So if you're not aware of DFS, just see how I code it and you will get it done. And the next thing, basically the next logic is about, so we move in levels. So at each levels we have to do this. So this is our algorithm. What we have to do, we need a data structure over here, which will be a vector of x and vector of y. So these are basically level nodes. What are the nodes at this level? Okay, so this we get from the queue. Whatever we have in the queue is actually present in that level, and here also we get it from the queue only. So yeah, that's fine. Now we have to process this queue only. So what we are going to do next, it's a part of the level. So here first we need to make two checks over here, like we have discussed earlier. First check is about elements in x vx should be there in vy. The second check is that by performing, okay, so yeah, second check is that by performing some swap operations, by performing some adjacent swap operations like this, can we make vx equal to vy. This is the pretty much logic. If no, then return false. Here also if no, then return false. And at the end we return true. So this is the overall logic, and now we have to implement it. So what is challenging is this swap thing. We need to think about the swap thing. Yeah, okay. So some nodes I talked about you, like so there is one thing which I missed over here. So basically, obviously we return true at the end, but before that we need to push the children to for the next stage. So that is at this level. So at each level we have to do that. So there is this third step over here, which is the most important step. The nodes which are not -1 I'm using it for null nodes where we get no nodes, right? Not -1, we push them in the queue, be it q1, be it q2, for the next level, and then we process with that only. All right, what we need next, now we need to code it up, and at the end we just return true. Okay, so this is the logic, and let me just do this. Okay, so this is the logic, and now we have to code it up, right? So let's move to the code editor where we will be coding the solution. And let's start. So we start with data structures over there. Let me take you to the code editor and we try to quickly code the logic. Okay, so let's go ahead and so obviously if we need to analyze the time complexity, we got 100 nodes in the range 100, right? So obviously BFS will take linear time only, and at each level what we need to do is basically this is a order n operation, checking each element in Vx is equal if it's there in Vy. So obviously here we can have sets which make these check operations even more efficient instead of vectors, and also the nodes are unique. And this checking of this swap thing is also order n only. So here it's 2n. At each level we are doing 2n, and there can be like at worst there can be of like order n levels, so n into n, it's n square solution, which is best suited for this because it will be passing the requirements of constraints. So now we start the coding. So here it's very important how we approach the solution. So we don't need to think about the language limitations at this moment. First we need to write the algorithm, whatever we thought over there. First we need to code it up in some pseudocode or like some code which is easier to write. Okay, so let me just switch off this layout. Okay, so yeah, we got it. Okay, so now let's go ahead and code it up. Let me zoom it a bit. Yeah, so first we will start with BFS. For that we need some data structures, and we all know the data structure for BFS is a queue which will be storing node, and we need two queues which will be q1 and q2, and obviously we're calling it like x and y, so let's call this qx and qi. And what we do, we at the starting point we push the root nodes here. You have to keep mind of the constraints here, like it's kind of zero, so there will be zero nodes over here, so we need to take care of that. So here we pushed the node root 2 basically over here. So one more thing is there. Yeah, so we push only if we have a valid node. Here also, if we have a valid node, then only we push in the queue. That makes sense. And then we just start the BFS logic over here. So we can take any, we can move it any queue, but there is a catch. So there is an edge case, like if any of the, I think that will be covered, but let me think. Yeah, there is a catch. Either we should push all the nodes to that queue, if even if it's null. So yeah, just we need to add this condition like this. QX, let's say if root 1 does not exist, or if root 2 does not exist. Here we just return false because that's the obvious case. Okay, so what if both of them are false? If both of them are null, in that case it's kind of a true case. Here it's given, right? So we need to add this kind of structure like, Okay, so we just need to do this, man. Like it should be an and. If both, sorry, if both of them are null, then we return true, and if either of them are is null, then we return false over here. So after this point, we are pretty much sure. I have one more condition, bro. This condition. Then also return false. So it's kind of done at this point. Now for the further levels, what we need to check is basically we need to check. We can move with any queue, right? And the moment where we kind of see any of the queue that is empty, if q1 dot qx dot empty, if qx is not empty, or qi, if any of these two is empty, we just going to quit it. If both of them are not empty, while both of them are not empty, till then we continue this logic, right? Now here we have two length of the current level, which is basically qx dot size, and integer ly is equal to qy dot size. And the first thing which we are going to do here is if the size is not equal, in that case it's a clear indication that we have to return false. So basically these are the level nodes, right? Now we need to make the level nodes thing over there. So what we can do in that case, we can have a set of tree nodes, and what we call them sx sy. Now we just need to empty that entire queue to these sets. And how can we do that? No, like set is an unordered thing, right? So we need to have the queues in the mind. Obviously we will be making some changes later on as well. So first thing first, see, sizes are same because we added this condition. Now we can directly move to that thing. Basically I'm asking to skip this part, the one condition. We just go ahead and check by swapping if we are able to do that. That is also the similar thing. So we can directly jump to that part. And how are we going to move? Okay, so how are we going to move is basically decided by Lx and Ly. Okay, so we will be changing the configuration first, because to match the things, we will be changing the configuration. That's true, we will be changing it. And for each of them, we grab like two nodes. It is guaranteed to be even. If it's not, in the first case, it would be 1. And in that case, what we need to do? Yeah, so basically that part is quite good in itself. So here, how can we move with this? Basically, I don't think set will be. Basically, the main problem which I'm facing at this point is that this queue, if we make any kind of swap operation, the queue will change. And then that will change the next level how we push the children, right? So why don't we store them in a vector? If we store them in a vector, in that case we can refer to them later on. Yeah, so we are going to do this. Okay, got it. So obviously we will be making a vector, and it will be a vector of tree node, and we call this Vx. Why not sets? Because sets do not hold this property of what we call it sequence. They are kind of stored based on their index values. They don't have the property like the order property. They are not ordered, they are kind of unordered. I mean, like, they do not record how we stored them initially, which becomes important because we are dealing with BFS, and here, to get that sequential thing, we need to do things sequence by sequence. Okay, so what we are going to do here is this. So since Lx and Ly are equal, so we are going to pop out every node. Top x equals to qx dot top y is equal to qx dot top, and then so this will be, sorry, this will be qy. And next what we need to do is basically now we are going to pop the top nodes. So q is by default, we all know it's first in first out. So we access the first element, store it in a variable, and then we are just asking it to pop the top one. Now what we do over here, we just push it in the vector which we are building. Why? Because we need to do some computations over here. So in this way we prepared this vector thing. Right. Now the queue is also empty. Now we are going to execute our main logic over here, which will be like, so the thing is, here at this point what we have all the nodes in a particular level. True, that's true. That's true. And what I'm going to do over here is very much kind of a unique idea that makes this easier to solve. We don't need to keep track of parents, right? What is that? Basically, I am saying that we move in this kind of logic. So the thing is, if we have, I'm saying that is we have always we have, no, we can have odd number of nodes in a level as well. And if we have number of nodes, in that case, yeah, I can go by expanding them by putting a -1 over there, or I can just store the parent of each node. That will make the thing easier to be done. Yeah, let's try with this thing. So what I'm saying is that I will somehow make this the number of nodes in a particular level even by putting -1 to the null nodes. So obviously this tree will be, in my case, it will be a full tree. Here the values which you don't see will be kind of doubled, right? So there will be -1. So here there are 2 nodes, in the next there will be 4, here it will be 8. So it will move like that. And if there are 100 such nodes, it will make it more worse, I guess. But yeah, there is some other approach as well, which I will be discussing later on, but I got no time in this video, I guess. Where I keep track of parents and just move by parents only. For that, we need to have a pair, and that comes with its own complications. Okay, okay, okay. Okay, so there's only one case. For the root node, there is only one case where Lx is equal to 1. In that case, what we are going to do? Okay, so Lx has vanished probably. I put it Ly. In that case, what I will be doing here is basically saying this: if yeah, so if root basically that is the thing over here. Yeah, it's only about the root nodes. So that might get pushed over here. So yeah, if we just do it this like this way, Vx of 0 val is not equal to Vx of 1. Sorry, it would be Vy of 0 dot val. You can also keep dot, but I'm not sure about the syntax. So here in this case, we just do that. We return false, not equal. Otherwise, we perform the code logic. Now, for all other cases, what do we need to do? Yeah, so we will be moving in this manner. It is guaranteed to be even. So I'm moving to two steps, right? You probably get that. And what I'm going to do over there is that is this thing. So basically there are two nodes in QX and QI. So first thing first, we have N1 and sorry, I'll just do like this. If we have X1, which is basically Vx of I, and we have X2, which is Vx of I plus 1. And I just do this for the other one, which will be of y. This will be of y. Okay. Okay. So first thing first, I have to make this y2. First thing first. First thing first. If I push all these x's, this x and y in a set, there should be only two unique elements. If that is violated, then obviously it's a exit thing. We cannot make that equal. Okay, so let's go ahead and do it one by one. So first compare x1 and y1. If x1 is not equal to y1, then you have to check if x1 is not equal to y2 as well. In that case, you return false. Make sense? Else, what we will do if they are equal, here you have to make a swap. Right? And yeah, and this swap should probably fix that. Yeah, so how we are going to swap it? So we are just going to do this. Oh, guys, we need a parent in order to make this swap possible. In order to swap these nodes, we need the parent. And who is the parent? The one we have left behind. Okay, how we can bring it back, because obviously from 2 we cannot access its parent 1, from 3 we cannot access its parent 1. So how we are going to facilitate the swap? It's obviously by doing this conversion, or wait, can we just change here, like we just swap 3 and 2's? We don't change in this tree, we maintain it in our queue. Will that work? Let me think. If 3 is here, there, if I change the order, yeah, it will work. Guys, it will work. I just swap in, not, I don't swap the actual values, we just swap the order, right? So we just use this inbuilt swap function, which will swap. What it will swap? It will swap I and I plus 1. Pretty much same, right? And now I have to check for the other guy. Similar setup. Yes, similar setup. Okay, so if they are not equal, if they're equal, it's peace, man. It's peace. Nothing to worry about that. So for the other guy, you have to make the similar changes. I have to compare it with y2. Okay, if it's not equal to y2, probably it's equal to y1. Probably it's not. If it's not equal to y1, then it's a very much bad thing. And else we just swap it. How we swap it? We swap it in the same way, and it will make the things work. So this way we have done the swappings, and at any point if we had such kind of anomaly, it was taken care of. Now it's time, very important thing is this basically, the building of the queue from these vectors. So for auto x inside vx, we're going with vx first. So if x dot val, which is this, is equal to -1, in that case, we are just going to push these two nodes. So what we are going to push over here, okay, so we are going to push a particular, oh, that also sorts the problem. No, no, it will be the same problem. Um, can I do that? Can I do that? Can I do that? So obviously, what I'm thinking is basically I need a tree node over here, which will facilitate everything. Tree node, and how we create it. I think I need to use new symbol over here, and I have to pass the value, right? We need to pass the value like this, and left right should be null. That works, right? Okay, so here we are. So here I did this. I just start with a value, and here what I'll do, node left is equal to node itself, and node right. Since there's a dummy node, I don't think there is some issue, any kind of issue with this. If I did this, then in that case what I can do over here is I don't need to worry about that. I can just simply go ahead and I can push that thing up. So it's basically this thing. What we do, we need to push qx dot push x car left, x left, and qy dot push, oh sorry, qx dot push. For y we will do it separately, x right. For y we are going to do the same thing, and yeah, obviously the -1 nodes are now taken care of. Okay, so there's a fundamental problem here. Yeah, they're not taken care of, right? So you have to consider them. If x left is null, basically is it's not defined. In that case, I need to do this qx dot push node, Otherwise, so I'll be doing it for the first time only. Otherwise, same goes for the other thing. If right not doesn't exist, then you just do this. Otherwise, you'll be doing this. What we will be doing here, we will be pushing the node. Okay, so let me copy this thing over here. This will be y. I can change this to y. It's kind of good. However, that was not required to change this y, but yeah, it's fine. Let's do it. Qy, and here we just make it y. And this is also y. Wait. This is also y. And here we get y as well. Yeah, makes sense. Yeah, it does. This is basically building for the next level. We build it. That is automatically taken care of. And what plan we had earlier, it was okay. So there is one more thing. It will keep going and going. Yeah, so we need to stop, right? Somewhere we need to stop. So we need to check if they're all minus ones. So I can just do this. Just make a check, which is equals to false. What I'll be doing, so in this case, it's there, else we are pushing this part. We're pushing basically these things, right? So I just do this. If x left is not equal to minus 1, uh, what we do here is basically is not equal to minus 1, or x left val right val is not equal to minus 1. In that case, we just return. So we just change this to check is true, right? Same goes for this part. Here also we want to make this as y. This is also y, and here we did that. And at the end, when we are ending these things, if check is false, break, we have to return false basically. Otherwise, we will be returning true. Yeah, that is it. Let me check if the logic is correct. So there is no top in Q. So what we need to do here is basically change it to front. So it is related to the PFS thing. Uh, so this is a syntax error. Probably forgot the syntax of queues. And what we get here is this error. Pardon me guys, this is pushed back. I was just writing the algorithm. The syntaxes we can fix later. Nothing to worry about that. one more compilation error which is about, okay, so which is about the same thing here. So it is not int, my bad. It is this. Makes sense. Oh, one more thing is there. Once we make this kind of swap, right? So this configuration changes, right? So we should no longer check with x2. We should redefine that. Yeah, after swapping, maybe x1 and x2 are changed. For us, x1 is equal to y1. If x1 is not equal to y1, then if x1 is equal to y2, then we changed. Okay, so it is equal to y2 basically. So why did we swap? What did I do here, man? This is really. So if x1 is equal to y2, so x1 is not equal to y1, x1 is not equal to y2 as well. So in that case, we did that. In case x1 is equal to y2, in that case, what we need to do? We need to send x1 back to that, and we can do that only if y1 only we can do that only if x2 is equal to y1. If it is not equal to that, then there is no point in doing this. Return false. And if they are equal, you need to check with this. They're equal, it's basically you need to check with that part, y2 part. And if any kind of swap happened at this place, what will that mean? That these two are already sorted. Because the swap was necessary, so if we go ahead and compare that, so this will be needed to taken care of. Yeah, now I think it's good. Member access within null pointer of tree node. So we accessed some member from tree node. From null boys we mentioned that. But wait, what are we pushing here? If they don't exist, we push this guy. If they exist, yeah, so I have set their left and rights to the same node, right? So it's kind of circle, right? Let me see. So the error which I got was this at this point. So this could be null. Oh, okay, got it. You have to make this check only if they are not null. Yeah, that will make it more longer, but who cares? So let's make that start left and this will be a one condition, and then we have x right and this will be the second condition. Here also we need to do the same thing. Here we will do this y left and here also we need to check if y right exists. So let's format it. Now run this code. I don't think there are more errors in this apart from the error in the logic. So my code returned a false. Why is it false? Can I get to know where it was returned false? Oh man, you don't have to do this, right? If check equals to false, you don't have to return. You had to just break and return true. Right, it will be a past solution, to be honest. But yeah, we need to be sure about that. For this, what I'm going to do, I need to add a custom solution, custom test case, which will be an extension of the first test case. And how can I do that? Basically, if I changed it, I need to make some more changes needed here. Okay, so there were two nodes, right? So yeah, basically it was kind of a game in itself. So it is not a simple case, it's a complex case. Okay, so I'm sure about the complexity, which is under control. I'm also sure about the code which I have written. Let's check if it passes the solution, passes the test cases. Whoa. So yeah, I think we had struggled a lot in this problem, but obviously it is making sense now. So, but the thing is that I am still using this much memory, which I am very much aware of, because I'm not storing the parents of the trees. If I store the parents, I don't need to expand all the nodes of the trees. What I'm doing in my solution is basically expanding each and every node of the tree. So I think if there are, if a single guy is watching this video, I will code that approach as well. If not, maybe I'll do it myself later on. Let me check if I'm actually streaming or not. So there is a guy who is watching this video. Maybe it's me only. If a single guy is watching this video, I will code that approach as well. If not,
Oh,
maybe I'll
sorry.
do it
Yeah,
myself
you're
later
fine.
on.
Yes, just started.
Let me check if I'm actually streaming or not. So there is a guy who is watching this video. Maybe it's me only. If a single guy is watching this video, I will code that approach as well. Let me just mute this man. Oh, so we really got someone watching this video. Okay, so the other approach which I was thinking was basically this part. So you see here I am, yeah, basically this part only. So here you see if a node is null, I'm still pushing it in the BFS queue, which is kind of increasing the number of nodes. Actually, there are 100 nodes, but let's say in some cases, if we have, wait, it is paused. Okay, so if we have kind of, let me just resume the session. Do you have anything in the comments? No. So yeah, so just I'll quickly talk about the solution and then we can simply talk about the other approach. So basically the other approach is okay, so for some reason this is not working. So what I was saying is that when the solution will get worse, it will get worse when we have this kind of tree. So let's say if we have one, two, three, four. So we have a tree which has one children only. And let's say if we have 100 nodes, so it will go all the way up to 100. And here we will be just for each level, what my approach will do will basically for the first level it will create one. For first level it will create just one level node, and if I as I go down it will start doubling it. So it will be like we need one memory over here. We'll be needing two memory, like by memory I means one memory I mean here is a memory to store the tree, and likewise we it will start doubling. So here it's 1, here it's 2, here it will be 4, here it will be 8, and here it will be 16. So it will move in that manner, and that kind of worsens things here as well, because this is also, this part is also, yeah, this part is also an order n approach, right? So yeah, if we include the parent, if we include the parent in BFS, this approach can be made much better. But yeah, since I have already spent a lot of time in this, I won't be doing it today. Okay, so I solve every day. Yes, I have just started, and probably you can get this recording. Alright, it's time to end the stream. I just dropped the streaming.